All right, guys, we're dealing with right now worksheet number 8, question number 9 on electric fields. You can see the question up here says 3 charges are in a straight row. The first charge is this value. Second charge is this value, which is negative. It's to the right of the first one, 60 millimeters to the right of the first charge. The third charge is positive, and it's 5 centimeters. Watch that. Okay, not only are they units that we have to convert, but they're not even the same units that we have to convert. One we got millimeters, one we got centimeters. That's not a huge deal, but just watch out for it, right? Because it's easy to miss that it's 2 separate units. We want to find the strength of the direction of the electric field 2 centimeters to the right of the third charge. So it's critical that we draw this picture here, and that we draw this picture correctly here. The first charge is positive, and its value is 2.50, positive 2.50 times 10 to the negative 2 coulombs. The second charge is negative. We're going to make that negative 4.00 times 10 to the negative 2 coulombs, and it is 60 millimeters to the right of the first charge. I'm just going to convert that to meters right now. 60 millimeters divided by 1,000 is 0.060 meters. So charge 2 is 0.060 meters to the right of charge 1. You label that as 60 millimeters, that's fine, as long as you convert it later on when you do your calculation. Now the third charge is to the right of the second charge. It's positive 3.00 times 10 to the negative 2. And it's 5 centimeters, or 0.050 meters to the right of the second charge. We want to find the field strength to the right of the third charge right here, 2 centimeters, or 0.020 meters to the right of the third charge. So what do we have present there at that point, 2 centimeters to the right of the third charge? Is there a positive charge there? Not that we know of. Negative? Not that we know of. As far as we know, there's nothing there. There could be something there, but if there is, we're not told anything about it. So we have to assume that there is nothing there. Now, we want to find the field at that point, the strength and the direction at that point. So what we're going to do is find the direction of each field at that point. Field caused by number 1, field caused by number 2, field caused by number 3. Number 1 is a positive. Number 1 is a positive charge. Ryan, if number 1 is a positive charge, does the field point toward the positive or away from the positive? Points away from the positive. So we're going to say E1. E1 is to the right, away from the positive. We're not so much thinking about right or left, we're thinking about toward or away. It's away from the positive, which just happens to be to the right. Now, as you're thinking about that, you're pretending that 2 and 3 don't even exist, right? Just pretend they're not even there. Visualize it if it's just charge 1 and the field pointing away from charge 1. Now let's look at number 2. 2 is negative. Does the field point toward or away from a negative? Toward the negative. So that means E2 is going to point this way, toward the negative, and that just happens to be to the left. So we get E1 to the right, E2 to the left. Now, Ashton, E3, the electric field number 3, is caused by a positive. Does it point toward a positive or away from a positive? Away from a positive. So E3 is going to be to the right, away from the positive. Make sense? Yes? Okay, let's calculate each of those fields, and then we'll worry about adding them together. We're going to say E1. Electric field number 1 is KQ over R squared. It's 8.99 times 10 to the 9 times Q. The value of charge I'm going to use is 2.5 times 10 to the negative 2 divided by R squared. What value of R do I use there for E1? What? Yeah, we got to add them all together. 0.06 plus 0.05 plus 0.02 is 0.13 meters. Don't forget to square that. When we do, we get a value of 1.3299 times 10 to the 10 newtons per coulomb. Hey, there's E1. We're going to do the same thing for E2, a little bit easier because it's closer. This is KQ over R squared as well. 8.99 times 10 to the 9. Again, times, this time the charge is negative 4 times 10 to the negative 2. Negative 4. Cash is at negative 4. Yeah, we drop the sign of the charge in the equation. Just make it positive 4 times 10 to the negative 2. And the distance here is the legend, Matt Peloso. The distance is 0.070. 0.070 meters. So we do the math on this one. It works out to be 7.3388. 7.3388 times 10 to the 10 newtons per coulomb. All right, the third one, E3 is also KQ over R squared. It's 8.99 times 10 to the 9. This is the easiest one because there's nothing to add together for distances. The charge here is 3 times 10 to the negative 2. And we divide that by the distance, which is 0.020 squared. We get an electric field there, E3, of 6.7425 times 10 to the 11 newtons per coulomb. Now, what do we do with these? You got to add them up, right? We're going to say the net electric field is equal to E1 plus E2 plus E3. E1 is 1.3299 times 10 to the 10 newtons per coulomb. E2 is negative 7.33. Why do we make that negative? Not because the charge is negative, but because we drew the arrow to the left. And E3 is positive 6.74. It's positive because it's on to the right. If we add those up, we get a net electric field of 6.14 times 10 to the 11 newtons per coulomb.